on this equilibrium model, and we did introduce what equilibrium was. So, what we're going to do is make sure everybody has graphed correctly, and that we understood what's on the x-axis, what's on the y-axis. We all have a title, we all have the correct unit of measurement and all such. So I want you to get that out and get ready to get a stamp for that, and then we will continue on with reversible reactions and all the stressors that accompany that, along with Le Chatelier's principle. Great. Let's see. We have time. Make sure you say seconds. You know what a snowball is. And then we have here an appropriate title, which would be force equilibrium. Okay, that was good. Oh, I like how you did that. Good job. And sometimes it's harder to figure out which ones connect if we do both at the same time. Like, so if I know, I'll be back before 7 o'clock.
I guess I was most of this back there, but I feel like if I walk in the door late after going through
Alright, so make sure you have your correct axis titles, and you can correspond with them on that. Are we supposed to have our phone?
No,
Okay,
I'm really lost in the
let me check that out for you. Good job. So number of balls. Driving force in equilibrium would be good. Time in seconds. Make sure those seconds in parentheses. And then maybe right now, once you fix that, you can go back and try to answer these questions. We went over those, I believe, at the beginning of class yesterday. So if we're having issues, maybe we can correspond with somebody else. We're gonna only take about 10 minutes to finish this up. I will come around and give everybody stamps. What you need? Pencil. There's fine right there.
I think they're reverse and forward.
So wait, the conditions, we didn't change the conditions, right?
No, we did not. Okay, so what we need here is we need to decipher between the two. Okay? You need titles and then the title here. Okay, great.
The solid one is the reactant.
Yes. Driving force, you can say round 1 or trial 1, trial 2, trial 3. For time intensive purposes, we are only gonna do the first graph right? So, once you've done that first graph, if you have time, start on the second and third and so forth. I know some people are already done with that third one, but I want to make sure everybody's at least cool with the first one. Okay, so the bottom, I want you to do it from 0 to 30, since we timed this for 30 seconds. And then your y-axis is going to be 0 to 50.
They email instead of text.
Since we had somewhere around 40-ish snowballs. Okay? And then when you graph, and those are gonna go 0 to 10, 20, 30, 40. And these ones can be 5. So 5, 10, 15, 20, 25. Okay? And then you're gonna plot your points according to this. So this is your x, that's your y. So you go over 0, up 26. Over 5, up 18. And then connect all those dots. Then you're gonna do a second one in a different color, and you're gonna do 0, and 0 is your first. Okay. Over 5, up 8. Okay. Yeah, good job with the title.
I can. I need my stamp. Driving force, number of snowballs, time in seconds. And this looks good. And then you have to decipher which one is which. So which one is the product and which one is the reaction.
Mango pie.
Yes, you may go potty. Sean, don't forget the pads over there on this, hanging up on the hook. Thank you.
You know, after every single calculus test we have, I mean, every single calculus test we have, he gets up when he's done and walks up to Pat and says, Pat, can I go potty?
What's up with him saying potty?
I don't know. Grown man, by the way. That is an 18-year-old. That's
This bottle?
Okay, it's okay.
Pat, can I go potty? Every single time we have a calculus test.
Stamp it.
Oh, yes. Let me go grab my stamp. By the way, I have had a Celsius and a Vietnamese coffee today.
Thanks.
So,
Drink water.
oh, thank you for reminding me, Lainey. I will grab my water.
I am on the top because I drink Monster every day. You know, I also bring with me every day a whole water bottle.
Have you ever had the Vietnamese coffee from the farmer's market?
I have not.
It is so good.
What does it taste like?
What's the
Besides
name?
coffee.
Well, they
This is.
over pour really strong coffee and they mix it with sweet condensed milk. So, and then they pour it over ice. So it's one of those iced coffees.
Ooh, that sounds good.
Yeah, I don't like hot coffee. Okay, you guys are doing a really good job with this. The main thing that we wanted to get from this, there was two things, right? I wanted you guys to make sure you were comfortable with graphing.
This is a test of the high school paging system.
Oh my God,
Testing
stop.
1, 2, 3. Test check. Page system 1, 2, 3.
I think the page system works.
Well, but I think how do they know if we don't tell them we heard it? So maybe I should go check my messages and see if maybe I need to respond to that. We'll check real quick.
Now I didn't hear it, you really did.
You can type it and stop it. So,
Okay. You know, you got a single letter K.
yeah, nobody really said anything about responding, so I don't know how they're gonna know their test works. But
I'm pretty sure they can hear it.
Maybe they have something to say
they don't
outside.
know in each individual classroom.
Oh, I guess.
Yes,
Let me check mine.
yes, I can.
Me too.
Okay.
You got those labeled, so that's good. So
Makia.
make sure you say number of snowballs there, equal driving force and equal period. Yeah, Lainey?
The specific heat capacity of liquid is higher than solid. That's true. But
The what is,
the specific heat capacity to turn from a liquid to a gas
yes.
is higher than to turn from a solid to a liquid. Is that
Yes.
because of the enthalpy of vaporization, or just because it takes more to break the bonds?
Pretty much it takes more to break the bonds.
It doesn't have to do with enthalpy.
Correct.
Okay.
I mean, enthalpy is a result of that.
So like, if I say that like liquid is to transition from a liquid to gaseous state takes more energy, and it's not because of the enthalpy of vaporization. That's like enthalpy of vaporization is a product of that. Okay.
Yeah, that would be a great way to say that. Okay, so I'm just gonna staple that for, stamp the first one. If you want to make your observations there until we're ready to start on the equilibrium, you can do that. To keep us moving forward. Does anybody else have any questions about what they're doing right now? Okay, you're just making observations basically. Okay, so think about the number of snowballs as the concentration. So we could actually interpret this, do math, and put this at hundreds, and do the math and figure out what this concentration, obviously it's 100%. But, so you don't have the number of snowballs.
Yeah, no,
Yours is just per concentration of what's increasing and decreasing.
That's exactly what I do each night, and then I brush it in the morning. That's it.
So which one is your product, which is your reactant? You might wanna tell yourself that. Okay, so why did the product start at zero? Product will start here. I think sugar does, because you should you start with 100%. Okay, so just wait. So reactant and product, and so this is where I say I feel like you just got them switched with your colors. Which you did it correctly. Yes, so, yes, that's what you did. So I think, hopefully there's not too much reprogramming about that. Okay, so we started with 100% of products. So we were on this side of the room. And we had all of the snowballs over here.
Yeah, and there's
Right?
zero over there.
Yes.
Okay.
Yes, does that make more sense now? Okay, you guys good? Let's see. Alright. More snowballs at a time, and make sure you put the seconds there.
That's what I didn't know what it was about.
Reaction. No, you got it.
Okay, cause that was before.
Because remember when we did this, we had all of the snowballs on this side of the room. You
I don't know what you're talking about.
Reactant. Yes, you're right. Did I just told you.
Well, if it takes one.
You said this is reactant?
Yeah.
Yes, you're right.
Wait, no, the blue is reactant, and the red is. Oh, that's right.
But it's wrong. It's supposed to be all reactant. Yes, 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 yes. Yes.
Sure.
Yes.
Positive.
Woo!
Okay.
Yes, 100%. Sorry, Braylon.
Everybody that I talk to has posters.
You have to go
I
potty
helped
too?
somebody make a poster.
Okay, you may go, but you can go after him. But we're gonna get started on this equilibrium model so quickly.
Yeah, we need to stand.
Guys, this equilibrium has a lot of, working parts.
Thanks, Teddy.
Your gigantic arm second. And which one is your product and which is your reactant? Yes. Yes. And so just label that, and you're gonna put a little red is the product. And that, and then you're good to go. Did I staple it? Did I staple the front part? Okay. I just said, oh, good job. Camille. I can stamp you now? Right. Now, yeah, you got the stamp, it's fine. Alright. I think we're ready to move forward now. 10 seconds. Okay, yep, good job. Right. Yes. My brain sometimes gets a little dyslexic and I think opposite, so I have to check myself.
When do you want us done with unit seven?
Cause she already looked at mine. She did an exchange.
11 to 14 class periods.
Got it. So 11 to 14 days.
About 2 weeks.
About 2 weeks.
It's closer to,
So by March. Before.
at the top of March, because we still have 8 and 9 to get through. I want to get through before spring break. So that all we have to do after spring break
Review.
is to hit that review, do some labs to kind of solidify what we learned, okay? We might go through a little bit, more reteaching on some things, and then that way I think we'll be in good shape. Real good shape. Yeah, I'm really proud of you guys. You guys have been really real. I did it. Okay, make sure you say number of snowballs and then you say time in seconds, okay? Because people need to know exactly what your graph is. Right? Graphs are supposed to tell the principle, but first, we need to do some defining here. We're gonna go back to the beginning. This won't take us long, but it's gonna take some laser focus, okay? There's lots of moving parts when we're talking about equilibrium. So, we've seen a reaction like this with this double arrow, okay? This means that it is a reversible reaction. We can produce reactants and we can come back and produce products, and this thing happens dynamically, okay? I'm gonna be doing lots of moving around because I feel like it helps you learn, because it helps me learn that way, because if I can think about direction when it comes to this, it's really important, okay? So all this bottom equation means is that it's these two equations mixed together, okay? We can take these reactants and make products. We can also take this product and make reactants, okay? That's all that means. But we are talking about rate and not amount of product or amount of reactant, right? Because remember from the law of conservation of matter, we cannot create nor destroy matter, okay? We learned that in our last concept. Now, there's really no net change, kind of just summed up this whole slide in my last response. We're talking about rate and not amount. Le Chatelier's principle tells us what conditions will move that direction, that reaction in which direction, okay? This is considered a forward reaction if it's the reactants producing a product. It's considered a reverse reaction if the products are producing reactants. Does that make sense?
Yes.
Okay. I like that. Okay. So, changes are stressors. We're going to call them stresses, okay? Those stressors are concentration, temperature, and pressure. Now, there are some rules and exceptions to those rules, just like anything else. So this is why
principles only apply every Tuesday on a blue moon.
yeah. Blue moon, not red moon?
Not red moon, like, it's ridiculous. Hess's law type stuff only applies in such specific scenarios.
Okay, so here's an example. I'm gonna move through this rather quickly. We're talking about blood pH and exercise. So if you think about exercising, it creates stress in your body. We're talking about biochemical reactions, okay? So it builds up acid in your body. And then you have a response. Your body has a certain response to that, okay? That response is taking in more oxygen. And it's also producing CO2 that comes out, okay?
You're doing awesome this
We
weekend.
knew that biology, we learned about homeostasis in biology, right? Right? You learned about homeostasis in biology. Doesn't matter how many students I have, I'm still teaching, yes.
I almost guessed the right amount of how many walk out.
You did?
I think I guessed correctly. I
was
said there was
sure.
only gonna be 4 and Luke's coming back, right?
Yeah, I said
Yeah.
7.
Okay.
I said 7 would bleed, 9 left.
Okay, I'm going to put this chart up here for just a minute where I need to go mark down those students that walked out. So I need to go just kind of like type out those names. If you guys could help me as I'm typing them out, that would be great. And then I'll continue on with this in just a
Do you
moment.
want me to teach while you write it down?
I got it. Let's see. It doesn't work. So I'm just gonna write it down on a piece of paper. Actually, you know what, Jackson, what would be helpful for me
Yes.
is if you just wrote them down on this piece of paper.
Okay.
A bunch of
John?
Pardon the interruption, just to remind your students, if you were leaving for the walkout, we are out the back on the on the bus driveway. Out the back doors to the bus driveway, thank you.
Who was that?
He seems so mad.
It's, right?
He sounds so upset.
Oh, no, maybe he's hoarse. Maybe he has a cold. Okay,
Sick.
so I'm gonna continue on with this. Our first stressor is concentration. Okay, we experienced concentration with the number of snowballs that we were doing in that activity yesterday. Okay, so the number of snowballs is representative of concentration. So hopefully we got a good visual of what that looked like when we're talking about driving force and equilibrium. With that being said, if we add a reactant, we're increasing that concentration of the reactant, right? If you increase the concentration on one side, your equilibrium shifts in the opposite direction. You're missing two. Jude, hold on. Here, let me see it. Emiliano, Alex, John, Lainey, Hope, Raylan, Isabella, Lily, and Camille. Thank you so much, Jackson. Okay, so as you see here, just on our chart, we have reactant. It could be either A or B, it doesn't matter which one it is. It's gonna proceed in the forward direction to go away from that, to relieve that stress, okay? Now the opposite is true if it is a product, okay? If you're adding that product on this side, right? You're shifting the reaction to the left, okay? That is a reverse reaction. Now, we just talked about adding product. Now we're gonna think about actually removing a reactant or a product. It pretty much does the opposite of what you would think it would be, like adding it, right? So if I remove a reactant, so if I remove A or B, okay, on this side, it's gonna wanna relieve that by adding more, okay? So it's gonna shift in that direction. Same goes for our product. If we take away some product, it's going to do what?
Disintegrate.
We remove some product, I think you were kind of busy when we were talking about this, but if I remove some product over here, it's gonna wanna shift in the forward direction,
Okay.
okay, to
Yeah.
replenish what I took away. Make sense? Okay, that's concentration change, that's the stress of concentration. Now let's talk about temperature. Temperature is our second stressor. Okay. First, we need to define some things. Exothermic reactions and endothermic reactions. That term is not new to us, right? Okay. If it's an exothermic reaction, we are having heat or energy as part of our product, okay? You see here there's 91 kilojoules. That's a unit of heat energy, okay? That's what KJ stands for. If you see that on the right, on the product side, that means it's product. It's an exothermic reaction. If you see that on the left side, it's a reactant. That means it's endothermic and it requires heat to proceed. So just like our concentration, if we were to add heat to an exothermic reaction, it's adding a product. So which direction will it shift?
Forward.
No, it's already, if I'm adding toward, if it goes in the opposite, sorry, it goes in the
Reverse.
yes. Okay, so I'm just trying to get you to kind of recall some of the stuff that we just talked about. I know it's just brand new, fresh in your
Oh.
mind.
So when it's exothermic and you add it's reverse, when it's endothermic you add it's forward.
Right, because heat is considered a product in an exothermic reaction, and if we add products, right, we have to shift in the opposite direction to relieve the stress.
if we add a reactant, which is heat in an endothermic reaction, we're gonna shift away from it, which is forward, yes. You're like left, right, forward. I'm like, okay. Yes, you got it though. Good job. Okay. This picture is I feel like it's very important and pertinent to understand our next stressor, which is pressure. So we have concentration, then we had temperature, okay? Concentration and temperature, they're kind of parallel one another, okay? So they kind of, I think of temperature and temperature and concentration the same, right? They're gonna shift in the same directions, okay? Pressure's a little bit different. We've got a little bit of, what do we call exceptions here? And we'll go through those in just a second. Now, I like this picture because it shows what pressure looks like. Now pressure here is less than the pressure here. Do we all agree in that?
Yeah.
Okay. What do you notice about the volume of these two pictures? Okay, which one is more volume? The one on the left, yes. Look at the arrangement of the molecules in there. Okay, on the one that's more volume, those same amount of molecules have more room to bounce around, less opportunity to make connections with one another. Okay, when they make connections with one another, they can create bonds, hence create what? Products, yes, good job. And then if we decrease the pressure like this, we're increasing the volume. So hopefully you've made the correlation that pressure and volume have an inverse relationship, okay? Because as we decrease the pressure, we increase the volume, right? This is gonna come at us when we are doing our unit on thermodynamics, but for now, we're going to focus on just the pressure, okay? We'll deal with volume later, but it's important for you to understand that there is an increased volume here with decreased pressure. Now, this is just the words I should have put up as I was talking, so. Here we go. Here are our stipulations, or what do we call it, exceptions to the rule. Now, pressure does not affect a system if you do not have any gas involved. So you have to have gas on both sides of the equation, right? You see solid over here, right? You see a solid and a gas over here, okay? The system doesn't care about pressure if there's not gas on both sides, right? Because it's not producing gas over here and back and forth, okay? So you would say that this equilibrium is unaffected because there's not gas on both sides. Next we have this equation. We kind of have to count the number of molecules we have on both sides because we actually want them to be different in order for pressure to affect its equilibrium. There's one molecule of N2 gas plus 3 molecules of hydrogen gas, okay? That's 4 molecules on the reactant side. There's only 2 molecules of ammonia gas on the right-hand side, okay? So that tells me if I add pressure to this system, it's gonna affect it one way or the other, right? And we know that from the previous slide, we know that increasing the pressure is gonna make those molecules bounce off each other faster and create more products. So this one favors the forward reaction if you increase the pressure. If you decrease that pressure, it's gonna go in the reverse reaction, reverse order, okay? Now, the last one, we have 1 molecule of hydrogen gas, 1 molecule of chlorine gas. It produces 2 molecules of hydrochloric acid gas, okay? That sounds pretty scary. there's 1 + 1 is 2 equals 2. Pressure is not going to affect this reaction at all. Any questions about that?
Nah.
No? Okay. Now, this is where we can go practice our Le Chatelier's principle. I will explain how to do this. I think it's page 31. What is your question?
Were teachers allowed to work out?
I knew nothing about this, so all I knew was some walkout was planned. I don't know why.
But you don't know why they're walking out?
I do now.
Uh,
I did not prior. Okie dokie. I'm gonna grab my paper because I did not bring it over here. Okay, now people can type in here. I can't type in here.
do you want me to take the note to the office?
Let me explain this first. Then I'll let you take it down. Or I can just do it during passing, it's fine. Okay, so everybody has out page 31? Okay.
Yeah.
Okay, so what this is practice with Le Chatelier's principle, which we just learned about. You have a reaction on the top, which was one of the first reactions that we learned about in slide 1. We have SO2 gas plus O2 gas has a reversible reaction with SO3 gas. Okay? On the left, you have a full list of stressors that's going to happen to this reaction. You have to predict which direction is favored, okay, by adding that stressor. It's going to be easier to predict what happens to the reactants and the products once we get that line finished. So what I want, I'm going to walk through how to do that, and I'm going to explain what happens to those reactants and products. But when you actually do it, I want you to do the direction favored first, because that will help you. I'll explain that here in a second. So if we were to add SO2,
Yep.
Teddy, is SO2 a product or reactant?
That's not
I'll show you.
a reactant.
Yes, but I want to show you so you know where to look. So this is the thing. So since everything's on the left-hand side, they're reactants. Everything on the right-hand side are products, okay? So if we are going to add a reactant, so first you have to identify whether that is a product or a reactant, okay? Then you can determine which direction it's going to go. Okay, so since this is a reactant, I know I'm gonna move from that reactant side towards that product side, okay? So that's why it says forward in your example.
Yep.
We put a dash or a line on the one that we're talking about, because that one doesn't matter, because we're talking about it.
Yep.
Once you decide what direction it's gonna go, if it's going in the forward direction, would our products increase or decrease?
Both.
If you're going, let me just repeat that, just think about it real quick, or not so quick, give me two. If we're going, say, these are the reactants, okay? These are the products. I'm moving this direction. Are the products gonna increase or decrease?
Increase.
Yes. I don't know why I turned around to do that.
No, that's good.
I kind of feel like, I don't know. It's just easier that way. Okay, so you've decided if it's a forward reaction, the products are going to increase, right?
Yeah.
What's going to happen to the reactants?
Decrease.
Yes, so you have to have that balance, right? So when one increases, the other one decreases.
Yeah.
Are you guys ready to practice this?
Yeah.
Yes.
Sounds like you are. All right, let's go. Do your direction favored first, and then decide what's going to happen to those reactants and products. I'll come around and I'll You guys can talk to each other about this if you need to, and I will come around and see if you need any help. I still can't type.
I was just doing
My
the
number
adding.
lock is not on, I can't type.
Are we just doing the adding right now?
What?
Are we doing the remove as well, or just adding? Like the removing part?
I think we do this.
You are going to, yours are gonna write down, in direction favored, you're gonna write either forward or reverse. And then on the section there for reactants, probably, yeah, increase or decrease, just like we said.
Oh, that's like if he wants to do this.
Oh, yes, I'm sorry. No,
Precision control.
no, Oh, you are correct, yes. Yes, that is right. Good job, Jackson.
Thanks.
This is the test of the high school paging system. Testing, testing, 1, 2, 3. Check testing, 1, 2, 3.
How about check this?
Okay, so how are you guys doing? I'm gonna check. Yes. Okay, so it kind of works opposite of F. So, yeah. How you doing, Teddy? Okay, so this one here, if you're saying that by adding a reactant, you are shifting away, so you're going forward, good job. But here, SO2 is a reactant. So if we're moving in this direction, we would decrease that. So whenever you have a forward here, these ones are decreasing, and this one is increasing. So wherever you say forward here, you would have increase here, wherever you have backward here, you have decrease here, and then the opposite is here. Is that helpful? This is kind of why I suggested doing this, all this first, and then you could fill in those easier. Okay. Jackson, why are you in your phone?
Cause I completed it, says.
Okay, well then, I would like you to move on to the next one then. We have a whole new set of, a whole new equation here. So, let me check it first, then you can move on. Sure. So, forward, reverse. So if we're adding some of this, we're moving away. So that one's reverse. That one, yeah. The second one. Oh, well, the second one that you wrote. Do you understand that part? I feel like you that is correct. But if we're reversing the reaction, going back to those reactants, this could not, there's no way this can increase. I feel like what I can do is I'll find you guys like a PhET diagram or something that we can manipulate, and you guys can see what this looks like, you know, other than just having a picture on my slide, you know? So we're gonna start out class tomorrow with that. I'll find that PhET diagram, we can visualize this. I do want you guys to try doing more of this. So our next equation looks like an endothermic reaction because we have heat. We have 12.6 kilocalories in our reactant side. So, and there's more working parts in this one, so it gets a little more complicated. So we will continue on with this tomorrow, okay? And then I'll give you that PhET simulation so you can kind of work with that a little bit, kind of help you understand this a little bit more. And we will do a review, let's see. And then we have an ocean acidification project we're gonna do, and we'll have a review, and we'll have our test on Friday out of all 3 concepts, okay?
Okay.
And you guys can tell your friends that had to walk out what's all happening, okay? And then hopefully you guys can kind of pair up with them tomorrow and just help catch them up to speed, because out of all the lessons, this was a tough one to miss. Okay, I mean, there was a lot of work to